goodness of fit test. So what is goodness of fit test? So whenever you hear goodness of fit test means we are comparing two distributions. Say for example, I have one distribution. So I have one distribution. Sorry, any distribution. So I have one distribution. Say normal. Okay. I think from the data we feel that this is a normal data, and now we will see that whether whatever the data we have, does it actually fit a normal distribution curve or not. So we assume that we make a hypothesis that this is a hypothesis test, right? That this should be a normal distribution from the observations that we have for the count of the data, and then we try to fit it on the existing PDF or PMF of a known distribution. That's why this fit word comes, that we are trying to fit a distribution, the observed distribution on the known distribution. So that's why this fit word comes, that how good this is fitting on a known distribution that we have, any distribution. I'm giving you normal because you know this. So any kind of distribution which is known, we try to fit the observed data based on the categorical count, and we try to fit it on the known distribution. Okay. So what is the goodness of it? Used to compare observed frequency count. So let me write it formally. It is used to compare observed categorical frequency count, whatever frequency is the count, observed frequency count of a category. Say for example, if I have a male, female, others, gender, right? So I will count for each category. What is the count? The observed frequency of each category count of a categorical variable. Okay, to a hypothesized. Okay, to a hypothesized or expected distribution. So I expect my distribution to be normal or any other distribution or t distribution, something variable, to a hypothesized or expected distribution. So I expect it to be certain distribution because the data I have I have observed. So I feel that this should be this, and now I can use this test to confirm whether the expectation and the data, they fit together or not. This is what it will give me. So this is a goodness of fit test, and the test statistic that we are using here is the chi-square test statistic that we have seen already. So test statistic is this one. So copy it as it is and paste it here. So this is your test statistic. Okay, let me make it different color. And what are these values? I have already mentioned, but I'll just write it formally for you. So OI is the observed count for ith category, and EI is the expected count. So we have I is equal to 1 to k for k categories, and then k is the number of categories. Okay, and now we have degrees of freedom also. So there was a parameter n, if you remember, here in the chi-square, right? In the chi-square this thing, distribution, this is n. So we also need this n. What is the degrees of freedom for this? So the degrees of freedom for this would be, so I'll write degrees of freedom is equal to, this is a k is the number of categories, so this will be k minus 1. You have seen this k minus 1. There's one more thing called minus m. Okay, generally this is equal to 0, and this m denotes the number of parameters estimated from the sample data, okay, to determine the expected probabilities or something, okay, or distribution. What is the distribution? So this is the number of estimated parameters estimated from sample data. This is the number of parameters estimated from sample data, okay, to determine the expected probability distribution, to determine expected probability distribution. Generally, this m is 0. We don't estimate any parameter. So we'll keep mostly this will be 0. And then this will be a number of categories -1. As discussed, the degrees of freedom will be the number of independent observations that will be impacting the variability of the data. Okay, observations or data points. Okay, so this is your chi-square goodness of fit test. So if you're since we are talking of goodness of fit test, let me tell you some more goodness of fit test. So there are other goodness of fit tests also. They are very popular, and that needs to be. This is for categorical data. What if you have a continuous data? Okay, that is more normal. So for that, the most common is your case test or Kolmogorov-Smirnov test or case test. This is used for. So what does it use? It uses your CDF or empirical CDF to the theoretical CDF. So basically it uses a CDF. CDF is your cumulative distribution function, the summation of PDF. Okay, it compares the using CDF of two distributions, roughly speaking. And the second one is Anderson-Darling test. Anderson-Darling. These are name of scientists or mathematicians who developed these tests. This is called AD test. So this is just an enhancement of the above case test. Okay, and then we have one more test called Shapiro-Wilk test or called SW test. So this is generally used for, this is specialized for normal distribution. When you want to compare whether a distribution is normal or not, then we use this Shapiro-Wilk test. This is specialized for normal test. So when we know that the data is normal, so this is specialized for normal test, then we go for Shapiro-Wilk test. But if we don't, if we have any other kind of other test, so mostly we start with this case test, Kolmogorov-Smirnov test. Okay, so these are also tests. Just look at the Wikipedia page and that will be like self-explanatory. So you will get a broad idea what it is. I just mentioned it because you should know that that is the chi-square goodness of fit test is not the only test, and that too is only for categorical data. And for rest of all the continuous data, you have this. Okay, so these are all around your goodness of fit test. So now we have talked a lot about goodness of fit. Now let's understand it using a question. I'll give you a very simple question. This will make you very clear. Okay. So we are talking about multinomial. So we'll see a simple case of that. That is binomial distribution. The simplest is toss a coin. We toss a coin, okay, 100 times, and we get heads for say 62 times, and tail is the remaining 38 times. Okay, and now I want to find it. I want to find whether it's a fair coin. I want to find whether it's a fair coin. So what are we asking here? So what is the underlying distribution for a fair coin? It is a uniform distribution, right? That probability of 0 and 1. Okay, even if it's continuous, so this is half, and if we are doing continuous, then this is 1. Okay, so every value between 0 to 1 has equal probability. So this is a uniform distribution. So we want to confirm whether this observation follows a uniform distribution or not. And here the uniform is only for 0 and 1, but it can have it can be for continuous. It can be like this, or if you have a PMF, then we have like this. Okay, on 0 we have half, and on 1 we have half. So this is your PMF. So these are the two masses, and if it's continuous, then this will be like this. This will be 1 will with the value here, and 1 is the breadth, because the area under the curve should be 1, total 1, not half. area under the curve should be always for PDF should be 1. This is continuous uniform, and if it's discrete uniform, then the sum of all the probabilities should be 1, and this is half here and half here, so this will sum up to 1. So the basic idea is that it is a uniform distribution or not. We want to confirm that, and for that we'll use the goodness of fit test. So let's see what all values we have got. So we'll do a hypothesis testing. So what is your null hypothesis? What is your null hypothesis? That both are same, means both the heads and tails is same, and it's a fair coin. Fair coin means status quo. Okay, nothing. So my probability of heads is equal to probability of tail, so that is equal, is equal to half. So whenever you have equal condition, that's your hypothesis or null hypothesis by default, and the alternate hypothesis is that not a fair coin, right? So that's what, if it is failing, then it will not be a fair coin. This is your alternate hypothesis. So what is my expected value of I if it is a fair coin under null hypothesis? I'm assuming this is, everything will be under null hypothesis only. All this OI, EI, okay, this is all is under null hypothesis only, under H0, assuming H0 is true. Okay, null hypothesis is true. So EI under null hypothesis, if it's a fair coin, then it should be equal to half, or have 100 times, right? So this expected value should be 50, that is 0.5 into 100. Half of the times should be heads if it's a fair coin. That's the expectation I have, because that's my null hypothesis. But what is the observed? Observed is that observed heads is 62 and observed tails, these are the two categories, I 38. This is the value, right? So we have two categories here, I is equal to 1 and I is equal to 0 and I is equal to 1, or I is equal to 1, I is equal to 2. These are the two categories, and these are the two observations. Now let's put it to the chi-square test. Chi-square calculated. Okay, this is equal to, and here degrees of freedom will be equal to no parameters we are doing. So number of categories is 2 minus 1, that is equal to 1. So chi-square test for 1 degrees of freedom, this is equal to sigma I equal to 1 to k OI minus EI whole square by EI. This is equal to, so we have two categories. So this, let's do one by one. So observed value for heads, so we'll have heads and tails. So we have 62 minus expected is 50 whole square by expected value of I is 50 plus 38 minus 50 whole square by 50. So this is equal to, this is 62 minus 50 is 12, this is 12, this is 144, sorry, plus 144, both the denominator same. I'll put this here, and if you calculate this, should come out to be 5.76, simple maths. So this is your test statistic. Okay, this is your test statistic. So 5.76 and degrees of freedom is equal to 1. So now we have to see and say, so this is your what we have done. What we have done, that we have our null and alternate hypothesis, and we decided that we'll go with the chi-square test because it is a goodness of fit test, and then we found out the test statistic value. The next thing we need is the alpha. So let's say alpha is equal to 5% or 0.05, that's my significance value. Okay, significance level, go away, significance level or value. Okay, that is my significance. So this is there. So now let's find the p value or the critical p value or t alpha for 0.05 and degrees of freedom is equal to 1. So we'll refer a chi-square table. So if you just search online chi-square table, you will get it. So let me see. So this is your chi-square table. This is a chi-square table. So I've just highlighted this here. So for chi-square 0.05, it is telling you what is the area under the curve here. Like it is showing you. If you see, this is highlighted here. Okay, this chi-square. So for chi-square for 0.05, for degrees of freedom, this df is degrees of freedom 1. So this will be 3.841. Okay, so let me take a screenshot. I can highlight it for you. Okay, let me paste it. So let's come back to the screen. Okay, so what is our alpha here? So let me make it bigger if it's not clear. So here if you see, my alpha here is 0.05. So this is the value. So let me highlight all of them. So this is your 0.05. What is the corresponding degrees of freedom? I have 1, and this is your 3.841, and here this is showing that this is the value under the curve. Okay, so I hope this is clear. This is a way to see. You just write chi-square table and you will get this. So for degrees of freedom, we got that the value should be the T alpha, sorry, the critical value. Critical value for this is equal to 3.84, and we'll just plot this way. This is right skewed. So the critical value here is 3.84, and we have got our p-value as 5.76. So what does it say? So my p-value here is this region. This is equal to probability of observing t greater than or equal to t observed. This is chi-square value in our case, and this is your critical value. Let me use a different color. So this is your significance level. Okay, so this value should be 5%. The area under the curve here is 5%. So definitely the area under the curve is less than 5% here. So it is not meeting the criteria. It is less than the significance level. So it is not so significant. So what we will do, we will say that we can reject the null hypothesis. Okay, because my p-value is less than alpha. This is your alpha, which is 0.05. So what was my null hypothesis? That the coin is fair. But from the observation and whatever the chi-square test says, that no, reject the null hypothesis, accept the alternate hypothesis that coin is biased. This is not fair or not fair. I hope this is clear. Okay, this is clear. Very simple. So we just did a test for whether it's a uniform distribution or not. Simple test. Okay, so this is your goodness of fit test. Okay.